Okay, good afternoon, guys.
Good afternoon, sir.
Sir. Good afternoon.
Okay, we'll start right away kay taas pa tong ano. Kinalang mo man nato ning ato ang reaction kinetics nga review. Dapat karon kung dili, pwede nato ni uswag pa ugma, no? I still have time, pwede pa ugma. Then the following week, start na ta sa ato ang designing, no? Okay? So, we'll start first with a prayer. I hope everybody already log in, no? Nakalag in ang tanan. Okay? In the name of the Father, and of the Son, and of the Holy Spirit. Dear Lord and Father of all, thank you for today, this afternoon. Thank you for ways in which you provide for us all. For your protection and love, we thank you. Help us to focus our hearts and minds now on what we are about to learn. Inspire us by your Holy Spirit as we listen and write. Guide us by your eternal light as we discover more about the world around us. We ask all this in the name of Jesus. Amen. Again, good afternoon, guys.
Good afternoon, sir.
Good afternoon, sir.
Okay. So today is 15. Okay. Makita ba ninyo ang kuan? Okay, makita ninyo? Ang attendance sheet nato makita.
Yes, sir. Makita ra.
Okay. So, Abarkis,
Present, sir.
Abrasaldo,
Present, sir.
ah, Arong,
Present, sir.
Belbistre,
Present,
Anjete,
Arong, sir.
Arong na si Arong.
Sir. Present, sir.
Okay. Barrios ag Belbistre absent. Kanyete,
Barrios,
Present.
sir. Naa, sir. Barrios,
Present.
sir.
Sir,
Barrios na si
present,
Barrios.
Anjet.
Present,
Barrios na
Present, Barrios, sir.
Belbistre na
Naa, sir.
Okay, kisa pa. Ansita.
Anjet, sir, present.
Okay, sorry. Caballero,
Naa siya, sir. Nangita pa daw siya siyang mic.
sige, sige. Castañares,
Present, sir.
Clemente,
Present, sir.
Hoyos,
Present, sir.
Takay,
Present, sir.
Glasa,
Present, sir.
Dinopol,
Present, sir.
Durham,
Present, sir.
Cario, Jan,
Present, sir.
Brique,
Present, sir.
Giliena, Giliena,
Present,
Figueroa, sir. Present.
Giliena, absent?
Present, Giliana, sir.
Okay.
Thank you.
Zarina,
Present, sir.
Sir, Figueroa, present.
oh, yes. Lagroma, Lagroma absent?
Wait, sir. Connecting, sir.
Connecting siya?
sir.
Okay. Leopando,
Present.
Luwab,
Present,
Luwab,
sir.
Lumibaw,
Present, sir.
Yuli,
Present Lumibaw, sir.
Present, Nyole, sir.
Orok. Orok absent?
Present, Morok, sir.
Okay. Vida,
Present, sir.
Palis,
Present, sir.
Pito,
Present, sir.
Res,
Present area, sir.
Andas, Daphne,
Present, sir.
Ponte,
Present Reponte, sir.
Ruben,
Present, sir.
Anoy,
Present sa ano, sir.
Leo,
Present, sir. Sinilio.
Suson, Suson, Baragwa, Toledo,
Present, sir.
Vergara,
Done, sir.
Yaon.
Sir, present, Susan, sir.
Suson, present. Sige.
Yes, sir.
Yaon. Wala
Nara daw
siya.
si Yaon, sir.
Okay.
Nangita pa siya sa mic.
Connecting pa, sir. Yaon.
So, 39. Attended na ba? Let's see. Yes, 39. 38 day. Including me. Okay, very good. Okay, we'll start right away sa ito ang discussion. So, we stop sa kung ano? Sa 71. 71. 71.
Sir, good afternoon, sir.
Yes? Kisa ron?
Yaon, sir. Present. Yaon, sir.
Okay. Yes, yes. Nainag-ingon.
Thank you, sir.
Okay, we stop sa aning slow and fast reaction mechanisms. Actually, class, I will not be discussing the PowerPoint. Ako na lang ni siyang i-upload in PDF form, no, sa ato ang Moodle. Sa Moodle na ko ni siya upload in PDF form. Ang video, diri lang nato kuhaon sa image team. Ari lang mo pag-download, no? Kay lisod magsige-tag-download sa Moodle, dugay kaayo. No, sa image, dali ra. Pwede ra siya ma-access dayon. Okay? Although dili kayo siya may quality, pero okay raman siya, no? I'm just going to discuss because this one kining atong slow and fast reactions nangita ko video nga mo adapt siya, no, mo adapt din siya. I did not make my own video kay wala ko time, no, so naani siya akong gi-appeal and then for this. Okay, so naagi naman nato ni sa ato ang previous discussion, no, sa kinetics. Okay, we have the fast and slow. Actually, we have the elementary reaction for this one, no? Or makasabot ta. So, so this one, no? So the rate laws for multi-step reactions, discuss po nato na siya diha. Sa ato ang kuan. Activation energy, we have to discuss also this one. Unsa ni siya? I believe you already know these things, but you have to review, no? Maybe you forgot data, no, or a file for this one, no. Okay, so this is the analogy for the activation energy. Anyway, ang atong PowerPoint ako taas kayo kay because I almost put everything na lang, no, para mas dali ninyo masabot. Okay, so reaction coordinate diagrams napod ni siya ato nang giapil to sa ato sa video. Arrhenius equation napod ni ato ko ning napoy discussion na sa video karon. Okay, Maxwell-Boltzmann distribution murag wa nato ni ma-appeal, no. Anyway, Boltzmann distribution, it is a law that states that the average amount of energy involved in its different direction of motion of an atom is the same. Okay, so mostly mauko ni siya sa gases, no, nasa gases siya, pero it doesn't mean nga sa gas gyud siya, pwede sa tanan nga phases, no, pwede solid, liquid, no, pwede siya. Okay, now what is the Boltzmann distribution function? In statistical mechanics and mathematics, Boltzmann distribution or tawagon pa nato na siya og Gibbs distribution, no? It is our probability distribution or probability measure that gives the probability that a system will be in a certain state as a function of that state's energy and the temperature of the system. Actually, nag-involve ni siya, related ni siya sa Arrhenius, no? Sa Arrhenius of activation energy. Okay? So, I'm not sure kung na-meet na ninyo ni siya, pero hopefully na-meet na ninyo ni siya kay niagi naman tag-reaction kinetics, no? Okay, so Boltzmann distribution, it shows molecular energies in a gas, no, at a constant temperature sa on chemistry, no, siguro sa chemistry, but different po sa physics, sa PChem, no, sa physical chemistry, no, because mogdeal po ta not only in the gases but also in liquids and solid, no. Now, in chemistry, most gas molecules have energies within a comparatively narrow range, no, meaning to say at a certain profile, at a certain system, no? Doon na known nga mga temperature, pressure, doon na siya energy, no? Comparatively narrow range lang, no? Ang every molecule sa gas, no? Now, the area that the curve gives the total number of gas molecules, mura man po ni siya og parehora sa activation energy nga curve, no? Different lang ang iyang kuan. So, ang equation nato diha, it involves entropy, no? Entropy and the microstate distribution. So, S as an entropy is equals to the Boltzmann's constant, the natural log of W. Okay? So, ang W diha is the number of different ways or microstates in which energy of the molecules and system can be arranged or energy levels. As I said kaganiha nga sa atong definition niya, it is a function of the state's energy, no? Remember nga ang kada molecule sa niya doon na siya enerhiya, na siya energy, no? Labi na mas sige siya og kapakong, meaning to say kung mas dool sila magsige siya kapakong mas taas ang iyang energy, okay? Mas taas ang energy. So, do you have the graph here? Ato na siyang ako ning apil sa ato ang pag-download aron makita ninyo. So, the minimum energy needed for reduction, do na ta siya margin, no? Gamay ra kay siya og kinahanglanon nga energy. So, this is kinetic energy versus the fraction of molecules. So, sa karga na sa molecules din ang kinetic energy. Okay? So, mao na ang iyang distribution niya. Okay. So, we have also the catalyst. You already know what is a catalyst. Okay, so we'll include po din sa atong discussion. Katarang Boltzmann muragwa na ko ma-appeal, no? Wa ko kita og video sa Boltzmann nga mo-adapt sa atong. Anyway, pangitaan lang nako na siya basta og di na to man karon, include nako tomorrow, no? Okay? So example sa catalyst is enzymes. Actually, enzymes og catalyst pareho ra na sila. The only difference is that enzymes is the catalyst in living things, no? Naa sa mga kuan, sa mga body, no? Nga naay kuan, naay kagaling kinabuhi, no? Enzymes ang gigamit na niya. Catalyst na ang gi-involve na niya sa mga inorganic crop. So catalyst na sa mga organic and ang enzymes na sa organic and then catalyst inorganic. So they are pareho lang na sila actually, no? Different lang ang ilahang nature sa ilahang dagan. Enzymes, organic, catalyst, inorganic. Actually, pwede na nato siya interchange, no? Bisag nag-involve sa ato ang kuan, like for example, nag-involve sa cells, no? Unsay mga catalyst, for example, sa ato ang laway, no? Unsa may atong catalyst gigamit diha, no? Unsa may nag-breakdown sa iyang foods. Saliva kanang saliva nato, nag-breakdown naman na daan sa atong food, no? Okay? So, unsay nga catalyst ang ato ang nag-involve diha? In other words, unsay enzymes, no, nga nag-breakdown na diha. So, mura na sa ngana. Okay? So, this one, mo niyang kuan sa kanang gitaw na tong substrate actually substrate is sa inorganic man na siya gitawag na siya reactant, no? Reactant na siya. Okay? Okay, so anyway, inorganic mostly nga to ang kuan naman sa inorganic, so wala kay nako nigi kuan ang sa enzymes pero naapil mo gud siya sa catalyst, no? Okay? So actually this is the catalyst na, no? Ang ato gining deal is this one, no? Kining mga reaction. The first one is the enzymes, no? So anita din mag doon natay kani mga example, no, sa ato ang video discussion. Okay? So we have catalytic converters. Okay. Okay. So we'll start with the video. This is not this is the video with this we I uploaded last meeting we have. So we start now, no, for this one. Okay.
Number 8. Which of the following straight line plots correspond to a first order reaction? Let's look at answer choice A and B. Both plots have A versus T, which corresponds to a zero order reaction. Here, the slope is positive K, and for this one, it's negative K. Now we know for a zero order reaction, the slope is negative. So answer choice B corresponds to a zero order reaction. Answer choice A doesn't correspond to anything. Now for a second order reaction, we're going to get a straight line plot if we graph 1 over A versus T. And the slope for this one is positive K. So answer choice C corresponds to a second order reaction. Answer choice D is what we're looking for. This corresponds to a first order reaction. We're plotting ln A versus T, and we have the correct slope. The slope is negative K. So answer choice D is the correct answer for this problem. Number 9. The rate of a certain reaction with units of molarity per second increases by a factor of 4 when A doubles and increases by a factor of 27 when B triples. Which of the following represents the units of the rate constant K for this reaction? Well, let's begin by writing a rate law expression. So the rate of this reaction is going to equal the rate constant K times the concentration of A raised to some variable times the concentration of B raised to some variable or number. Now let's focus on A. When A increases by a factor of 2, the rate increases by a factor of 4. So when A doubles, the rate goes up by a factor of 4. So would you say it's zero order in A, first order in A, second order in A, or third order in A? Well, 2 to the what power is 4. We know that 2 squared is 4. So this tells us that it's second order with respect to A. Now, looking at the second part of the problem, it says that when B triples, or when it increases by a factor of 3, the rate of the chemical reaction increases by a factor of 27. So 3 to the what power is 27. We know that 3 to the third power is 27. 3 times 3 times 3 is 27. So it's third order with respect to B. Now, what is the overall order of the reaction? The overall order of the reaction is the sum of these two exponents. So it's fifth order overall. Now that we know the overall order of the reaction, we could use that shortcut technique to get the units of K. Recall the units of K is m raised to the 1 minus n, where n is the order of the reaction, times t raised to minus 1. So n is not 4, n is 5 rather. And the time is in unit of seconds, so this is going to be s to the minus 1. We simply replace t with whatever time unit we see in the reaction rate. So it's m raised to the negative 4 s to the minus 1. Let's save this answer. So if you were to ever forget this formula, here's another way in which you can get to this point. So in the rate law expression, isolate k. To get k by itself, we need to divide both sides by this. So we're going to get the rate constant k is equal to the rate of the entire reaction divided by a squared times b to the third power. So at this point, what you want to do is you want to plug in the units. The unit for rate is molarity over seconds, or you can say molarity times seconds to the minus 1. The unit for A is molarity, but it's squared. So you can write that as m squared or simply m times m. So that's for A. For B, it's m to the third power. So I'm not going to split it for that one. The reason why I split this into m times m is because I want to cancel one of the m's. So we can see that we have m to the 4 left on the bottom. 1 plus 3 is 4. Now we can move this to the top, and then we get the units of k as being m to the negative 4 s to the minus 1. So you get the same answer as what we got here, but this is just simply a shortcut technique. But you can always do it this way if you want to, if you ever forget. Now, this does not look like any of the answers that we have here. So we need to adjust our units. Molarity is moles over liters. This is moles to the first power, liters to the first power. We're going to move liters to the top. So m to the first power is moles to the first power times liters to the negative 1 power. Now, m to the negative 4. What we're going to do is we're going to write that as m to the first power raised to the negative 4. Because when you raise one exponent by another, you need to multiply. 1 times negative 4 is negative 4. So now we can replace m to the first power with what we have here because it equals m to the first power. So we're going to get moles to the first power times liters to the negative 1 raised to the minus 4. Now we're going to distribute negative 4 to these exponents. So first we have 1 times negative 4, which is negative 4. and then -1 times -4, which is +4. And typically, the variable with the positive exponent is usually written first. So m to the -4 can be rewritten as L to the 4 times moles to the -4. So now all we need to do is add our seconds to the -1. So m to the -4 times s to the -1 is liters to the 4th power times moles to the -4th power times seconds to the -1 power. So we can represent the units of k like this or like that. But looking at our answer choices, we have it in this form. Therefore, answer choice C is the correct answer. Number 10. What is the overall order of a reaction with the units liters cubed, moles to the -3, seconds to the -1? So with this problem, we're kind of going backwards here. So let's see if we can do this. We know that molarity is moles over liters, which is the same as moles to the 1st power times liters to the -1. Now, if we were to raise both sides to the -1, let's say if we were to raise this to the -1 and that to the -1, we'll get that m to the -1 is equal to -1 times -1 is +1, so that's liters to the 1st power, and then 1 times -1 is -1, moles to the -1 power. So you may want to be familiar with these expressions. So moles to the first, molarity to the 1st power is moles to the 1st power times liters to the -1. But molarity to the -1 is liters to the 1st power, moles to the -1. And in this example, notice that liters has a positive exponent. So liters cubed moles to the -3, what is that equal to? Well, if we factor out an exponent of 3, we'll get liters to the 1st times moles to the -1 raised to the 3rd power. So these expressions are equivalent. We just factored out 3 from the exponent. Now, these two are the same, so we can replace what's here with m to the -1. So we have m to the -1 raised to the 3rd power. So this is m to the -3. So liters cubed moles to the -3 is m to the -3. So now let's write everything that we have here. Liters cubed moles to the -3, s to the -1, that's going to be m to the -3 times s to the -1. Now let's set this equal to our general equation, m raised to the 1 minus n times t to the -1. So we don't need to worry about this. We know the time is in seconds. What we need to do is set these two equal to each other so we can solve for m. So m to the -3 is equal to m raised to the 1 minus n. Now, since m is the same, we could set the exponents equal to each other. So -3 is equal to 1 minus n, and let's subtract both sides by 1. -3 minus 1 is -4. If -4 is equal to -n, then we just got to multiply both sides by -1, and we'll get that positive n is equal to 4. So we could say that This reaction is fourth order overall. So answer choice E is the correct answer. Now, what exactly is an elementary reaction? An elementary reaction is one in which the coefficients of the reactants represent the order of each reactant in a rate law expression. So let me give you an example. So let's say that we have, let me rewrite that, A turn into B. The rate law expression is going to be K times A raised to the first power, because the coefficient of A is 1. And so whenever the order of the reaction is the same as the coefficient of the reaction, this reaction is an elementary reaction. Now, it's also known as a unimolecular reaction because it only takes one molecule for the reaction to get going. Now, let's look at another example. A plus A turns into B, which is the same as 2A turns into B. What do you think the rate law expression will be for that reaction? So the coefficient is a 2. So the rate law expression is going to be K times A raised to the second power. And so this is considered a bimolecular reaction because two molecules must collide in order for the reaction to occur. So let's try this example. A reacts with B and produces C. So what I want you to do at this point is I want you to write the rate law expression that corresponds to this reaction, and at the same time, determine the molecularity of the reaction. Is it unimolecular, bimolecular, or even termolecular? So the coefficients are 1. And so for this to be an elementary reaction, the rate law expression has to be A to the first power and B to the first power. So rate equals K times AB. Now the overall order is 2. It takes two molecules to collide in order for this reaction to get going. So this is known as a bimolecular reaction. Now let's look at another example. Let's say if A reacts with 2B to produce C. Write the rate law expression that corresponds to that elementary reaction and determine the molecularity. So the coefficient for A is 1. So the rate law expression is going to be K times A raised to the first power multiplied by B raised to the second power. So it takes 3 molecules to get the reaction going. So the molecularity is termolecular. So we have a termolecular reaction because we need 3 molecules to collide. Now let's look at this reaction. A plus B plus C turns into D. So go ahead and write the rate law expression. So all of the coefficients in this example for all the reactants are 1. So the rate is going to be K, A to the first power, B to the first power, times C to the first power. So the overall order is 3. So once again, we have a termolecular reaction. Here's another example. Let's say if 2A reacts with 3B plus 4C. Write the rate law expression. So the rate is going to be K multiplied by A squared times B to the third power times C to the fourth power. And so that's all you need to do if you want to write the rate law expression for an elementary reaction. In this video, I'm going to show you how to identify the intermediate and the catalyst in a reaction mechanism. So consider this example where A plus B reacts to produce C and D. And in the second step, D reacts with E to produce B and F. So in this reaction, what will you do to identify the intermediate and the catalyst? Now, to identify the catalyst appears on the left side first and then shows up on the right side. And the catalyst is not part of the overall reaction. The intermediate appears on the right side first and then shows up on the left side later. And it's also not in the overall reaction. Notice that B can be canceled and D can be canceled. So the overall reaction is A plus E, which turns into C plus F. So the catalyst appears at the beginning and at the end of the reaction, but it's never consumed, it's never used up. Notice that B is first produced and then, it's consumed first and then it's produced later. So B is the catalyst. It shows up on the left side first and then it shows up on the right side second. So make sure you understand that the catalyst is consumed first and then it's produced later on in the reaction. And that's how it's never used up. Now the intermediate is the other stuff that was canceled. The intermediate appears on the right side first and then shows up on the left side later. So D is the intermediate. It's produced first and then it's consumed later. The intermediate doesn't show up at the beginning or at the end of the reaction. It's somewhere in the middle of the reaction, so you really don't see it. But the catalyst is present at the beginning and at the end. Now let's consider another example. A plus B yields C and D. And then C plus E produces F and G. And there's going to be a third step. F plus A makes B plus E. So given these three steps, identify the intermediate and the catalyst. And just so you know, there's going to be two catalysts and two intermediates in this example. So let's find out what cancels. Notice that B cancels. So is B a catalyst or is it an intermediate? What would you say? Now B shows up on the left side first, and then later it shows up on the right side. So it's consumed first and then it's produced later, which makes it a catalyst. Now let's look for the next species that cancels. Notice that C cancels as well. C appears on the right side first and then shows up on the left side later. So it's produced first and then consumed later, which means C is an intermediate. Now, what else do you notice? Notice that E can be canceled. So E shows up on the left side first, and then it shows up later on the right side. So E is consumed first and then produced later. This means that E is a catalyst, just like B is a catalyst. Now next, we have F. So F appears on the right side first and then shows up on the left side. So F is produced first and then consumed later, just like C is produced first. And so F is an intermediate. So hopefully these two examples gives you a good understanding of how to identify a catalyst and an intermediate in the reaction mechanism. Now, if you want to write the overall reaction, on the left side we have A plus A, which makes it 2A, and on the right side, D plus G. And so this is the overall reaction. And make sure that the catalyst and the intermediate, they're not present in the overall reaction. So A, D, and G cannot be a catalyst or an intermediate. In this video, we're going to go over the Arrhenius equation, where K, or the rate constant K, is equal to A times E raised to the negative EA divided by RT. So what do these variables mean? A is the frequency factor. A is equal to Z times P, where Z is the collision frequency and P is the steric factor. But for the most part, for a typical chemical kinetics question, you really don't have to worry about A or Z or P. EA is the activation energy. That's how much energy you need to get the reaction started. We're going to talk a lot about that. Now, R is the energy constant, and it's equal to 8.3145, and the units are joules per mole per Kelvin. So therefore, temperature is measured in Kelvin. You don't want to plug in the Celsius temperature in this equation. The activation energy has the units joules per mole. It has to match with the units of R. Now, we need to understand the relationship between temperature and K and activation energy. But before we do that, you need to know how K plays a role in the rate law expression. Let's say if we have this rate law expression, rate is equal to K times A. Is this a first order reaction, second order, or is it a zero order reaction? What would you say? Now, the exponent of A is 1, so it's a first order reaction, which means that if you double the concentration of reactant A, the rate of the reaction will double. If you quadruple the concentration of A, the rate will quadruple. So anytime you increase the concentration of a reactant, if it's first order or second order, the rate will increase. Now, if it's a zero order reaction, if you increase the concentration of that reactant, the rate will not increase if it's zero order. Because let's say if you doubled it, 2 to the 0 power is 1. Now, if you double or if you increase the rate constant K, what's going to happen to the rate of the reaction? Will it increase or decrease? If you increase the rate constant K, the rate of the reaction will go up. Now, as we mentioned from the Arrhenius equation, K depends on the activation energy, which is EA, and it depends on the temperature. So if you can increase the temperature, the rate constant K will go up. However, if you decrease the activation energy, the rate constant K will also go up. Now, typically, when you increase the numerator, the value of the whole fraction goes up. But since it's on the exponent and since there's a negative sign, it's kind of opposite to that usual trend. So it turns out when you decrease the activation energy, the rate of the reaction goes up because K goes up. Now let's draw a potential energy diagram. So here we have the reactants, the products, and this is the transition state, also known as the activated complex. The activation energy, or at least the forward activation energy, is the difference between the energy of the reactants and the activated complex. The reverse activation energy is the difference between the activated complex and the energy of the products. Delta H, the enthalpy of the reaction, is the products minus the reactants. Now, what's going to happen if we add a catalyst to this reaction? What would a catalyst do? Now, you know a catalyst speeds up a reaction, but how exactly does it do that? Well, what a catalyst does, it lowers the activation energy. And it does so by providing the reaction an alternative pathway, another way to get to the products. And so that's how it lowers the activation energy. By the way, that reaction, is it exothermic or endothermic? Anytime the products have less energy than the reactants, they're low in energy, it's an exothermic reaction. Now, anytime you add a catalyst, the activation energy decreases. When the activation energy decreases, the rate constant K goes up. And whenever K goes up, the rate of the reaction goes up as well. When you increase the temperature, the rate constant K goes up. And therefore, the rate of the reaction will go up as well. Now, if you increase the concentration of a reactant, if it's first order or second order, and if it's not zero order, then K will stay the same. K is not affected by the concentration. However, the rate will increase if you increase the concentration of the reactant, because the rate depends on K and the concentration of A, if it's a first or second order reaction. So if you increase the concentration, or if you raise the temperature, or if you add a catalyst, you can increase the rate of the reaction. So now let's say if we start from this equation, the Arrhenius equation. What we're going to do is we're going to take the natural log of both sides. Starting from this equation, we're going to come up with a few other equations where if you're solving a problem, it might be useful to know those equations. So right now, we're going to have the natural log of K is equal to the natural log of A times E raised to the other stuff. Now, a property of natural logs can allow us to separate a single log into two logs. For example, ln A times ln, or ln A times B is equal to ln A plus ln B. So this is going to be like A and this is going to be like B. So we're going to separate it into two separate natural logs. So on the right side, we're going to have ln A plus ln e raised to the negative ea over rt. Now, another property of logs is you're allowed to move the exponent to the front. So this is equal to 2 natural log a. So let's take this exponent and let's move it to the front. So right now we have ln k is equal to ln a, and then it's going to be minus ea over rt times ln e. The natural log of e is 1, so that's going to disappear. And I'm going to switch these two. So what we now have is natural log of k is equal to negative ea over rt plus natural log of a. Now I'm going to put this in slope-intercept form. So ln k is equal to negative ea over r times 1 over t, which is the same as ea over rt. So this is like y, and this is mx plus b. It's in slope-intercept form. So ln k is y. The slope is negative ea over r. M is the slope in the slope-intercept form equation. And 1 over t is x, and the y-intercept, which is b, is ln a. So if we were to graph this function, since ln k represents y, we can put that on the y-axis. And 1 over t represents x, so we can put that on the x-axis. And the slope is negative, so we should get a straight line, but going down. And so, therefore, as 1 over t increases, ln k decreases, which means that k decreases. If ln k goes down, k goes down as well. So, if t increases, t is the reciprocal of 1 over t. That means ln k increases, which means k goes up. That's why we can say that as you increase the temperature, the rate constant k goes up, and the rate of the reaction goes up as well. Now, there's some other things to know about this equation. And one of those things that you want to know is the slope. We said that the slope, which is m, is equal to negative ea over r. So if you ever need to find the activation energy is negative r times the slope. So if you can find the slope of this line by doing rise over run, or by using the equation y2 minus y1 is equal to x2 minus x1, well, you can calculate the activation energy. But using that equation, we're going to get another equation. So here's what we're going to do. Let's replace m with what it equals, negative ea over r. So negative ea over r is equal to this thing, rise over run. Now y is associated with ln k, so it's going to be ln k2 minus ln k1, which is like y2 minus y1. Now x is associated with 1 over t. So x2 is going to be 1 over t2, and x1 is going to be 1 over t1. Now, let's make some space. Now keep in mind, ln A plus ln B was ln A times B. Now it turns out that ln A minus ln B is ln A divided by B. So using that fact, ln K2 minus ln K1 is ln K2 divided by K1. And if so we have that, and then 1 over T2 minus 1 over T1. And if we multiply both sides by R, or negative R, these will cancel. And so the activation energy is equal to negative R times this whole equation. Now you might have seen this equation differently. Perhaps you've seen this equation like this. ln K2 over K1 is equal to negative EA over R times 1 over T2 minus 1 over T1. If you rearrange the equation, you can get this equation. This is like the standard form of the Arrhenius equation. Now, if you need to solve for K, here's what you need to do. Let's say if you have ln A equals B. The base of ln is E. E raised to the B is equal to A. So you can change it to this equation. So using that fact, this natural log has a base E. So E raised to everything on the right side is equal to everything inside. So that means that K2 over K1 is equal to E raised to the negative EA over R times 1 over T2 minus 1 over T1. And if we multiply both sides by K1, this is how you could solve for the rate constant K2. So K2 is equal to K1 times E raised to the negative EA over R times 1 over T1 minus 1 over T2. And make sure, if you want to find the rate constant K, the activation energy must be in joules per mole. Don't plug in kilojoules or you will get the answer wrong. And keep in mind, 1 kilojoule is 1,000 joules. So to go from kilojoules to joules, multiply by 1,000. If you need to go from joules to kilojoules, divide by 1,000. So now you know how to find the rate constant K, and we use the other equation to find the activation energy. So now, sometimes you may need to find the temperature. So let's see if we can rearrange the equation to get the temperature. So let's start with this equation. So in addition to the last form, you also want to remember this form of the equation. So let's multiply both sides by R over EA. So on the left side, we're going to have R ln K2 over K1, and then it's going to be divided by EA. On the right side, well, let's add the negative sign as well. So negative R. So the negative will cancel, R will cancel, and EA will cancel on the right side. So we have 1 over T2 minus 1 over T1. So what I'm going to do now is I'm going to take this term and move it to this side. So 1 over T1 is negative on the right side, but it's going to be positive on the left side if you add 1 over T1 to both sides. So 1 over T1 minus R ln K2 divided by K1 divided by EA is equal to 1 over T2. So therefore, if we raise both sides to the negative 1, 1 over T2 is going to flip to T2. So here's the other form of the equation. If you need to calculate the temperature, use this. It's going to be 1 over T1 minus R ln K2 divided by K1, which is equal to, well, divided by EA, and then raised to the minus 1. So that's what you need if you need to find the temperature. Let's put all the equations together. And if you need to find the rate constant K, use this equation. It's going to be K1 times E raised to the negative EA over R, and then 1 over T2 minus 1 over T1. And in order to find the activation energy, we said that the activation energy is equal to R ln K2 divided by K1. There's a negative sign in front of the R, and it's going to be divided by 1 over T2 minus 1 over T1. So now you have the three forms of the equation. So if you need to find the temperature, use the first one. If you need to find the rate constant K, use the second. And if you need to find the activation energy, use the third. And that is it for this video. So thanks for watching, and have a great. In this tutorial, we're going to talk about factors that affect the rate of a reaction. So the first factor is the nature of the reactants. The second that influence the rate of a reaction is the concentration. Whenever you increase the concentration of the reactants, the rate of the reaction goes up. There's going to be more collisions, and so that's going to just increase the reaction rate. And of course, you've seen this expression, the rate law. Let's say for a first order reaction is K times A. So if you increase the concentration of A, the rate of the reaction will go up. Now, if you're dealing with gases, if you increase the pressure, the rate of the reaction will go up. It's equivalent to increasing the concentration because you're going to have more molecular collisions. Now, the third area is for solids, and that is surface area. For a solid, only the atoms on the surface of the solid can participate in the chemical reaction. The ones in the interior of the solid are not exposed to the other reactants, so they can't react. So for solids, if you can increase the surface area, you can increase the rate of the reaction. Now the fourth area is adding a catalyst. Whenever you add a catalyst to the reaction, a catalyst lowers the activation energy. And by lowering the activation energy, you can increase the rate constant K. And K affects the rate of the reaction. So when K goes up, the rate of a reaction goes up. So a catalyst, it lowers the activation energy by giving the system an alternative pathway. The fifth area is temperature. Everything goes faster when you increase the temperature. Whenever you raise the temperature, the rate constant increases, and therefore the rate of the entire reaction goes up. So at high temperatures, the molecules are moving faster, and so there's going to be more collisions, which leads to a greater reaction rate. And also, the molecules have more energy, so they can collide with sufficient energy to break chemical bonds and form new ones. Now consider this reaction. Let's say that hydroxide reacts with the tribromide ion to produce the hypobromide ion and two bromide ions plus H2O. And let's say that all of this is dissolved in water. Now what's going to happen if we increase the tribromide ion concentration? What's going to happen to the rate constant and the rate of the reaction? Now the rate of the reaction depends on the rate constant and the concentration of the reactants. The rate constant depends on the activation energy and the temperature. So if you increase the concentration of one of the reactants, the rate will increase, but it won't affect the rate constant K. The reaction will proceed faster. Now let's say if we increase the volume by adding water. What's going to happen in this case? Adding water will not affect the rate constant K, but it will affect the rate of the reaction. As you increase the volume, the concentration of the reactants decreases, and so the rate will decrease as well. Now, what if we increase the temperature? What's going to happen? If we increase the temperature, that's going to increase the rate constant K, which is dependent on temperature. And so the rate is going to increase. Now, what if we decrease the volume by evaporating water or allowing water to evaporate? If you decrease the volume, the concentration of the reactants will go up. And so the rate of the chemical reaction will go up. Now, finally, what if we decrease the pH of the solution? What's going to happen? Will the rate increase or decrease? Now, if you decrease the pH of the solution is becoming more acidic, so you're increasing the H plus concentration. Now, as you add acid to the solution, the acid will react with hydroxide to produce water. And so adding H plus will decrease the concentration of hydroxide, which is one of the reactants. And if you decrease the concentration of the reactant, the rate is going to decrease. So if you decrease the pH and make it more acidic, you're going to decrease the hydroxide concentration, and that's going to slow it down. However, the opposite is also true. Let's say if you increase the pH, that means the solution is becoming more basic, which means the concentration of the hydroxide ions is going up. And so if the concentration of the reactants go up, then in this reaction, the rate will increase. So when you're dealing with pH changes, think of how it affects the H plus and the OH minus concentration. And if they're part of the reaction, then that's going to affect the rate of the reaction. In this tutorial, let's talk about the collision theory model. So what's the basic idea behind the collision theory? The basic idea is that for molecules to react, they have to collide. If they don't collide, there's not going to be any chemical reaction. If there's no physical contact between these molecules, nothing's going to happen. So molecules must collide in order to react. The second thing is they have to have the correct molecular orientation in order for a reaction to proceed. So to illustrate this, let's say if we have hydroxide. And hydroxide is going to react with methyl bromide, CH3Br. Now, bromine is more electronegative than carbon, so it bears a partial negative charge. And carbon is less electronegative than bromine, so it's partially positive. The element that's more electronegative is going to pull the electrons toward itself, and that's why bromine has the partial negative charge. So hydroxide, since it has a negative charge, it's attracted to the carbon in methyl bromide. So it wants to attack this carbon, thus expelling the bromide ion. And so this will create methanol. So if it approaches from the back of the methyl bromide, if it attacks from the carbon side, it has the correct molecular orientation. So the reaction is going to work. Now let's say if it approaches it from the other direction. So let's say this is methyl bromide and hydroxide is coming in this direction. Well, the reaction is not going to happen. Hydroxide is repelled by the partial negative charge of the bromine atom. And so when two negative charges come together, they're going to feel a force that's going to repel them. And so that's going to prevent the reaction from occurring. Whereas when hydroxide attacks from the carbon side, the negative charge on the hydroxide is attracted to the partially positive charge on the carbon atom, and that electrostatic force of attraction accelerates them together, which favors the collision of those two molecules. And so if the two molecules do not have the correct molecular orientation, the reaction is not going to happen. But if they collide with the appropriate orientation, then the reaction is going to happen. So in order for a reaction to occur, molecules, they have to collide. And two, they have to collide with the right orientation. Now, the third thing is that they need enough energy. Because if the temperature is low, even though these two may be attracted to each other, if the hydroxide ion doesn't move with enough momentum, it's not going to be enough to knock off this bromide ion. So it has to have enough energy to attack the carbon atom and expel the bromide ion out of that reaction to create methanol. So there's three things that is required for a reaction to take place. The molecules must collide, and they have to collide with the right orientation, and they have to have sufficient energy to break some bonds and form some new bonds. Now, this leads us into energy diagrams. So on the y-axis is the energy of the system. On the x-axis is going to be the reaction coordinate. Here we have the reactants, and here we have the products. The top is the transition state, also known as the activated complex. In order for this reaction to occur, the system has to have enough energy. The reactants need to gain enough energy. There's something called activation energy, which is the difference between the energy of the transition state and the energy of the reactants. If the reactants do not have enough energy to overcome the activation energy, the reaction will not happen. So if they can't get above this hill, there's no reaction that's going to take place. So they have to have enough energy to get over that hill. And so that minimum energy to get the reaction started is the activation energy. So even if a molecule collides with the right orientation, if they don't have enough energy to make it to the activated complex, then the reaction is just not going to happen. So one way you can get up there is by increasing the temperature. Whenever you increase the temperature, the rate of the reaction increases. The fraction of molecules that can reach the activated complex will increase. Now, one thing I want to specify is this is known as the forward activation energy. There's something called the reverse activation energy, which is the energy difference between the products and the transition state. So in this example, it's easier to go this way than to go that way. Now, the next thing you need to know is that notice that the difference between the energy of the products is greater than the energy of the reactants. Whenever the energy of the products is greater than the reactants, what you have is an endothermic reaction. In order for this reaction to occur, energy has to be put into the system. An exothermic reaction looks like this. The energy of the reactants is going to be greater than the energy of the products. So this is an exothermic reaction. Now, initially, you got to put in energy to get to the activated complex, to get the reaction started. And once you overcome that barrier, then a lot of energy is going to be released. So you got to put in a small amount of energy to get it started, but you're going to get a large amount of energy once the process is started. And so that's an exothermic reaction. Now let's talk about the Arrhenius equation. K is equal to Zp E raised to the negative Ea over RT. Now Z is known as the collision frequency. If you can increase the collision frequency of a reaction, the rate of the entire reaction will go up. P is the steric factor. And this has to do with the fraction of collisions that have the right orientation. So this is a number between 0 and 1. And it depends on the nature of the reactants. Now this part, E, which is the inverse of the natural log function raised to the negative Ea over RT, that represents the fraction of molecules that have sufficient energy to get the reaction going. So notice that it depends on temperature and activation energy. So if you want a reaction to occur, there's two things you can do to help it, to make it work. You can increase the temperature, and that can give the molecules the energy they need to overcome that barrier. As you increase the temperature, the rate of the reaction will increase. The second thing you could do is add a catalyst. Whenever you add a catalyst provides an alternative pathway for the reaction, and by doing so, it lowers the activation energy, which increases the rate of the reaction. Now, the last thing we need to talk about is the product Zp. Zp is equal to A, which is also known as the frequency factor. It's the product of the collision frequency and the steric factor. So now let's put this all together. Now let's consider a first order reaction where we have rate is equal to the rate constant K times the concentration of A. And we know that the rate constant K is equal to the frequency factor times E raised to the negative EA over RT. And the frequency factor can be replaced with the collision frequency times the steric factor, and then times this. So Z, the collision frequency, represents the total number of collisions per second that's occurring in a reaction. P, the steric factor, which we said was between 0 and 1, that's the fraction of molecules with the proper orientation. Or more specifically, that's the fraction of collisions that are occurring with the proper orientation. So you can think of P as the probability that two molecules will collide with the right orientation. This portion here, which we describe as the fraction of collisions with sufficient energy, you could also think of it as the probability that two molecules that are colliding will have enough energy to overcome the activation barrier. So you can think of these two values as probabilities or fractions. So if Z is the collision frequency and P is the probability that two colliding molecules will have the right orientation, A represents the total number of collisions per second that's occurring in a reaction with the right orientation. Now, if we multiply the frequency factor by the fraction of molecules having sufficient energy, we can thus come up with an understanding of the rate constant K. So we can say that the rate constant K represents the total number of collisions per second having the proper molecular orientation as well as sufficient energy needed to overcome the activation energy barrier to get the reaction going, to convert the reactants into products. So the rate constant K takes all of those factors into account. Now let's talk about what happens when we increase the concentration of the reactant A. As we increase the concentration of the reactant, there's going to be more collisions. The number of collisions will increase, and therefore, the rate of the reaction will increase. Now, what about if we increase the temperature? If we increase the temperature, the average kinetic energy of the molecules will increase. So molecules are going to be moving faster. The molecular speed of the molecules will increase as well, and therefore there's going to be more collisions. And this too will increase the rate of the reaction. Now you can think about it another way too. In this formula, the temperature affects the rate constant K. Now the temperature is in the bottom of the fraction, and typically when you increase the denominator of a fraction, the value of the fraction goes down. However, notice that we have a negative exponent. And so because of that, when you increase the temperature, it has the effect of increasing K. It's like a double negative. You could think of it that way. When you increase the temperature, the rate constant K goes up. The fraction of molecules having sufficient energy to overcome the activation barrier increases. And when K goes up, the rate constant goes up as well. And let's show this with a distribution curve. So we're going to have energy on the x-axis, and we're going to have the number of molecules on the y-axis is not moles, but molecules. And we're going to have two curves. One at a lower temperature, which we'll say looks something like this, and another curve, which I'll draw in blue, at a higher temperature. So this one will be, let's say, at a temperature of 300 Kelvin, and the other one will be at a higher temperature, we'll say at 500 Kelvin. And somewhere along the x-axis, we're going to have EA, the activation energy. So anything above EA represents the fraction of molecules having sufficient energy, sufficient collision energy, so to speak, enough so that they can overcome the energy barrier to make the reaction go in. And let's put that in green. So in green, that represents the fraction of molecules at 300 Kelvin having enough energy to make the reaction go. But in red, which encompasses the area in green as well, that represents the fraction of molecules having enough energy to overcome the energy barrier to also make the reaction work. But notice that at 500 Kelvin, the fraction of molecules that have enough energy is greater than the fraction of molecules at 300 Kelvin. It's significantly greater. And so that's what happens when you increase the temperature. When you increase the temperature, the average kinetic energy of the molecules go up. So therefore, the fraction of molecules having enough energy to make the reaction go, that fraction increases. And so if more molecules have more energy to get the reaction going, the overall rate of the reaction will increase. Now let's talk about what's going to happen if we were to add a catalyst to the reaction. What do you think is going to happen if we introduce a catalyst? A catalyst has the effect of lowering the activation energy. Now here's a visual description of that. So this is a potential energy diagram. We have potential energy on the y-axis and the progress of the reaction on the x-axis. So let's say we have something that looks like this, where this represents the energy of the reactants, the products, and this is the transition state. For a catalyzed reaction, it would look something like this. So this is the uncatalyzed reaction. And this is the catalyzed reaction. The activation energy is the difference between the energy of the reactants and the transition state. But notice that when you add a catalyst, the activation energy decreases. A catalyst achieves this by providing a reaction with an alternative pathway. It actually changes the reaction mechanism. It allows the reactants to become products by taking a different route, so to speak. So that's how the catalyst can lower the activation energy. It helps the reaction find an easier way to go from reactants to products. Now notice that activation energy is in the numerator of that exponential fraction, whereas temperature is in the denominator. Now we know that an increase in temperature leads to an increase in the rate constant K. So what happens if we increase the activation energy? Well, it should have the opposite effect. It should decrease K. T is in the denominator, EA is in the numerator. So if increase in T leads to an increase in K, increase in EA will decrease K. Likewise, the reverse is true. If we decrease the activation energy, the rate constant K should go up. And that's what happens. When you add a catalyst, the activation energy goes down, the rate constant K goes up, and so the overall rate of the reaction increases. So those are some ways in which you can increase the rate of a chemical reaction. So to summarize, if we increase the concentration of the reactant, the rate is going to go up. If we increase the temperature, the rate of the chemical reaction will go up. And if we add a catalyst, the activation energy will go down and the rate of the reaction will go up. So those are some different ways in which we can increase the rate of a chemical reaction. You can increase the concentration, raise the temperature, or introduce a catalyst to speed up the reaction. Now let's write down some equations that you'll need to know in order to solve problems. So you're already familiar with this one. The rate constant K is equal to the frequency factor times E raised to the negative EA over RT. Here's another one that you should be familiar with. The natural log of the rate constant K, that's equal to negative EA over R times 1 over T plus the natural log of A. Now, in this form, this is written in slope-intercept form. So y corresponds to ln k. The slope m corresponds to negative EA over R. X corresponds to 1 over T. And the y-intercept, B, is ln A. So if you were to graph y versus x, where y is ln k, so we'll put that on the x-axis, the y-axis, and 1 over t is x, so we'll put 1 over t on the x-axis. You're going to get a graph that looks like this. It's going to be a straight line plot, but notice that the slope is negative. So the slope of this line is going to equal negative EA over R. And the y-intercept, which this is where the graph starts from, that's going to be ln A. So for problems associated with this equation, where if you have a plot of ln k versus 1 over t, just know that you can find the activation energy from the slope of the graph, and the y-intercept is equal to the natural log of A. So you could find the frequency factor from the y-intercept. Now R is 8.3145 joules per mole per Kelvin. So because R has unit joules and moles, the activation energy, which is typically reported in kilojoules per mole, when you use it in these formulas, it needs to be in joules per mole. So you need to convert it. So when reporting the activation energy, you want your answer to be in kilojoules per mole, But whenever you plug it into one of these formulas, you need to convert it to joules per mole. So make sure to be aware of that. Now the slope m is equal to negative EA over R. And the slope is y2 minus y1 divided by x2 minus x1. ln k is on the y-axis, 1 over t is on the x-axis. So if y is equal to ln k, we could say that this is ln k2 minus ln k1, all divided by 1 over t2 minus 1 over t1. So that's going to equal negative EA over R. Now let's say if we have ln A minus ln B. Using the property of natural logs or logs, we can convert this into a single log expression by writing it like this, ln A over B. So we can write this as a single log expression as well. We could say that that's ln A, that's ln K2 over K1. And this is 1 over T2 minus 1 over T1. And that equals negative EA over R. Now, if we want to get activation energy by itself, we can multiply both sides by negative R. If we do that, R will cancel on the right side as well as the negative sign, and we'll get an equation for activation energy. So the activation energy is going to be negative R ln K2 over K1 divided by 1 over T2 minus 1 over T1. So you could use this equation to calculate activation energy. Now you might see a variant of this equation. Sometimes this negative sign will be distributed to 1 over T2 minus 1 over T1. And that'll basically flip the order of T1 and T2. So this is also equal to positive R ln K2 over K1. And if you distribute the negative sign, negative times negative 1 over T becomes positive 1 over T1. And then here this will be negative, so minus 1 over T2. So you might see it in that format too. So just be aware of that. But if you have the negative sign, it's going to be 1 over T2 minus 1 over T1 instead of the reverse. Now let's go back to this equation. Make sure to write this equation, by the way, because you're going to need it to solve problems. Now, instead of multiplying both sides by negative R, let's multiply both sides by this term. If we do that, we'll get a different equation. We'll get this one, ln K2 divided by K1 is equal to negative EA over R. And we're going to move this to the other side, times 1 over T2 minus 1 over T1. So that's another form of the Arrhenius equation that you might see it in. Now, what we're going to do at this point is we're going to put both sides of this equation on the exponent of E. So I'm going to put all of this on the exponent of E and all of this on the exponent of E. Because E is the same and these two are equal to each other, both sides of this equation will be equivalent. Now, the base of a natural log is E. So on the left side, these two will cancel. And so we're just going to get K2 over K1 is equal to everything that we see here. Now, if we multiply both sides by K1, we can get an expression for K2. So you want to write down this formula because sometimes you need to calculate a new rate constant at a new temperature. So that new rate constant K2 is equal to K1 times E raised to the negative EA over R times 1 over T2 minus 1 over T1. So this is the second equation that you want to write down. So you have an equation that will help you to calculate the activation energy, and this equation will help you to calculate the new rate constant given a new temperature. Now let's go back to the equation that we started with on this screen. All right, that's as far as my software will let me go back. Now sometimes you need to calculate the second temperature. So what we're going to do is we're going to isolate T2. To do that, we're going to multiply both sides by negative R over EA. So those will cancel. And we're going to have negative R ln K2 divided by K1 over EA. That's going to equal 1 over T2 minus 1 over T1. So we're going to move this to the other side where it will become positive. So we have 1 over T1 minus R ln K2 over K1 over EA. That's equal to 1 over T2. Now we're going to raise both sides to the minus 1. 1 over T2 raised to the negative 1 power is just T2. So we get this equation. T2 is equal to 1 over T1 minus R ln K2 over K1 over EA. And this is raised to the negative 1 power. So this will help you to calculate the second temperature if you know the second rate constant and if you know the activation energy. So those are some formulas that you want to use when solving problems associated with the Arrhenius equation, activation energy, the rate constant, and things like that. Now let's go ahead and put these equations to good use. So we're going to work on a few practice problems. So take this one for example. A certain reaction has an activation energy of 50 kilojoules per mole. The rate constant at 25 degrees Celsius is 0.0039 minutes to the minus 1. What is the value of the rate constant at 75 degrees Celsius? So first, let's make a list of what we know. So we have the activation energy. It's 50 kilojoules per mole. The rate constant, which we'll call K1, is 0.0039. And that's at a temperature of 25 degrees Celsius, which we'll need to convert to Kelvin. So add 273 to 25, that gives you 298 Kelvin. Our goal is to calculate K2, and the second temperature is 75 plus 273, so that's 348 Kelvin. So what is the formula that will help us to calculate K2? It's K2 is equal to K1 times E raised to the negative EA over R multiplied by 1 over T2 minus 1 over T1. So anytime you need to find the rate constant at a different temperature, that's the formula that you want to commit to memory. Now K1, we know it's 0.0039. The activation energy has to be in joules. So we got to multiply 50 by 1,000. So it's going to be 50,000. And then it's 1 over T2, which is 348, minus 1 over T1, which is 298. And then divide that by R. R is 8.3145 joules per mole per Kelvin. You don't want to use the gas constant for R, 0.0826. It's not going to work for this equation. So if you type this entire thing the way you see it, or if you do it one step at a time, you should get this answer. K2 is 0.0708. So notice that K2 is greater than K1. 0.07 is greater than 0.003. Now this answer makes sense because the second temperature is higher than the first temperature. And as you increase the temperature of a reaction, the rate constant will increase. And when the rate constant goes up, the rate of the chemical reaction will go up as well. And so that's it for this problem. In this lesson, I'm going to explain how to calculate the units of the rate constant K. So let's start with a zero order reaction. So rate is equal to K. Now there's a formula that can help you to find the units of K. It's equal to m raised to the 1 minus n times t raised to minus 1. M is for molarity, T is some unit of time, which could be seconds, minutes, or hours. So let's say the rate is given to you in units of molarity per second. So you know that time is in seconds. Now this is a zero order reaction. There's no A, B, or chemical reactant there. So for a zero order reaction, N is 0. So the units is going to be M, 1 minus 0, and then replace the time with seconds. So it's m times s to the minus 1, which you could write that as molarity per second. Now keep in mind, molarity is moles over liters, or you can write it as moles times liters to the minus 1. So you can leave the unit like this, or you can write it as moles times liters to the minus 1 times s to the minus 1, which is the same as moles per liter per second. So there are many ways that in which you could describe the unit, but I'm going to leave it like this and like this, because on a typical test, you might see it like that. Now let's work on another example. So let's say if we have this particular rate law expression, rate is equal to K times A, where that is the concentration of A, and it's raised to the first power. So it's first order with respect to A, and it's first order overall. And let's say you're given the units of the rate of the reaction, and it's moles times liters to the minus 1 times minutes to the minus 1. So notice how the unit of rate is written. So for K, we want to write it in a similar fashion. So let's start with the formula. The units of K is going to be molarity raised to the 1 minus n times the time raised to the minus 1. So it's first order overall, which means that n is equal to 1. So it's going to be 1 minus 1, and the time is in minutes. So we can replace t with minutes. 1 minus 1 is 0. So it's m to the 0 times minutes to the minus 1. And so anything raised to the 0 power is 1, so we can get rid of this. So in this example, the units of k is simply minutes to the negative 1 power, or 1 over minutes. Now here's another example. This time it's first order with respect to A and first order with respect to B. 1 plus 1 is 2, so it's second order overall. And let's say the rate expression is given to you in terms of the units molarity per hour. So I'm going to write the units of K in a similar way, using molarity instead of moles per liter. So let's start with a formula. So it's going to be m raised to the 1 minus n times t raised to the minus 1. So this time, the units of time is hours as opposed to seconds or minutes. And because it's second order overall, n is 2. So it's going to be 1 minus 2, and then hours to the minus 1. So 1 minus 2 is negative 1. And so what we have now is we have molarity on the bottom because it's the minus 1, and hours is in the denominator as well. Now keep in mind that molarity is moles per liter. So we can replace capital M with moles per liter. Now I'm going to multiply the top and the bottom by liters. And so the unit is going to be liters on top divided by moles per hour. So that's how I'm going to write it. Now if you write it like this, liters to the first power times moles to the negative 1 times hours to the negative 1 is still correct. You can write it that way if you want. Actually, before I get rid of this page, I want to show you how to get the answer without using the formula. So if you ever forget what the formula is, here's what you need to do. In the rate law expression, isolate K. So that means we need to divide both sides by AB. So K is equal to rate over A times B. And then replace everything with their respective units. So the rate is in molarity per hour. And the concentration is always going to be in molarity. So the concentration of A is in molarity and B is in molarity. So molarity per hour, you can write that as m to the first power times hours to the negative 1. And it might be easier to do it that way. So notice that we could cancel m. Now I'm going to take this m and move it to the top. So it's going to be m to the first power times, actually, not to the first power, to the negative 1 power. Whenever you move something from the bottom to the top, the exponent changes sign. So it's going to change from positive 1 to negative 1. So it's m to the negative 1, hours to the negative 1. So you can leave it like that. Now keep in mind that molarity is moles per liter. So m to the first power is technically moles to the first power times liters to the negative 1. So if we multiply all the exponents by negative 1, m to the negative 1 is going to be moles to the negative 1 times liters to the positive 1. And we got to use this one for this example. So I'm going to replace m to the negative 1 with liters to the first power times moles to the negative 1 power. And then we have hours to the negative 1. So this gives us the same unit that we had in the last example. So the formula works, and it's up to you to decide which method works better for you. Now let's work on another example. This time I want you to use the formula, and I want you to confirm your answer by solving for k. So rate is going to equal k times a to the first power times b to the second power. So it's first order with respect to a, second order with respect to b. So it's third order overall, which means that n is equal to 3. And let's say that the unit of rate, or the rate of reaction, it's going to be moles to the first power times liters to the negative 1 times, let's say, days to the negative 1. It's a very slow reaction. So go ahead and use the formula to get the units of k. So it's going to be m raised to the 1 minus n times t to the minus 1. So we can see that the time is in days. So we're going to replace t with days instead of seconds, minutes, or hours. And n is 3. So it's m raised to the 1 minus 3, and then days to the minus 1. So 1 minus 3 is negative 2. So if you want to, you could leave the answer like this. If you have a multiple choice test, you have to adjust the answer in a way that matches your multiple choice answers. So you can leave it like this, or if you want to change it, that's cool. So keep in mind that molarity to the first power is moles to the first power times liters to the negative 1. Now I have molarity to the negative 2. So I'm going to raise each exponent to the negative 2 power. So I'm going to multiply 1 by negative 2. And so this becomes m to the negative 2. And then this is also 1 times negative 2. So this becomes moles to the minus 2. And negative 1 times negative 2 is positive 2. So moles to the negative 2, I can replace it with this. So I can write my answer as liters squared times moles to the minus 2 times days to the minus 1. So you can also write the answer like this if you want. Now, if you want to write it as a fraction, everything with a positive exponent, put it on top. So we have liters squared. Everything with a negative exponent, move it to the bottom. And if you do that, the exponent is going to change from negative to positive. So it could be moles squared on the bottom times days to the first power. So you can write this as it's liters squared per mole squared times days, or times a day. So you can also write it like that. Now, let's solve for k. So to get k by itself, we'll need to divide both sides by this expression. So k is going to be the stuff on the left, which is the rate of the reaction, divided by the stuff on the right except k. So that's a to the first power, b to the second power. So we already have the units of the rate. So it's moles times liters to the minus 1, which this part is molarity. So I'm just going to replace that with m for now. So I have molarity times the days to the minus 1. Now A is in units of molarity. B is in units of molarity, but it's squared. So it's going to be m to the first power squared, which is m to the second power. So I can cancel these two. And if I take this, move it to the top, then what I have for k is going to be m to the minus 2 days to the minus 1. So we got this answer already. And as we said before, m to the minus 2 is basically moles to the minus 2 times liters to the positive 2. So we can write it as liters squared times moles to the negative 2 times days to the minus 1. And everything that we did before, you can just repeat it at this point. So as you can see, you could get the same answer. And you just might find this method easier. And for those of you who simply like to use the formula, you can use the equation if you want to. So once again, just pick whichever method is easier for you. In this video, we're going to talk about types of chemical reactions: synthesis reactions, decomposition reactions, combustion reactions, and then single and double replacement reactions. So what is a synthesis reaction? This is a reaction where you have multiple reactants combining to form a single product. So A plus B turns into AB. Let me give you some examples. So if we take zinc metal and react it with oxygen gas, this is going to turn into a single product, zinc oxide. Now this reaction is not balanced, and we really don't need to do it for the sake of this video. But notice that we have two smaller components and we're generating a single product. That is a synthesis reaction, which is also called a combination reaction. Zinc and oxygen are pure elements. Zinc oxide, that's a compound. It's made up of two different elements. Here's another example. If we were to take barium oxide, which is a compound, and react it with carbon dioxide, which is another compound, this will give us a single product at low temperatures known as barium carbonate. This is also a synthesis or combination reaction because we're taking two smaller components and combining it into a larger product or a single product. So that's the basic idea behind a synthesis reaction. Now, before we go into the next type of reaction, I do want to mention, for those of you who are watching my videos and who haven't subscribed yet, feel free to take a minute, hit that subscribe button, and don't forget to click on that notification bell. That will be greatly appreciated. Now let's get back to this video. Decomposition reactions. A decomposition reaction is the reverse of a synthesis or combination reaction. So in this case, you're starting with a single reactant, AB, and you're going to break it up into two or more products, typically A plus B. So a good example of this is magnesium nitride. So this is an ionic compound, and when heated, will decompose into its component elements, magnesium and nitrogen gas. So here we have a single product breaking down into multiple fragments. So that is a decomposition reaction. Another example is the use of calcium carbonate. If you heat up calcium carbonate, you can represent the heat phrase with, the word heat with a triangle. If you heat up calcium carbonate, it's going to decompose into calcium oxide and gaseous carbon dioxide. So that's another example of a decomposition reaction. It's simply the reverse of a synthesis reaction. The third type of reaction that we need to talk about is a combustion reaction. Combustion reactions typically involve some compound containing carbon, hydrogen, and or oxygen. And typically, the most common example of these reactions is that you take that compound, react it with oxygen gas, and you're going to get two products, carbon dioxide and water. So here's an example of one. Propane C3H8 reacts with oxygen gas to produce gaseous carbon dioxide and liquid water, depending on the temperature. If the temperature is above 100, that's going to be steam, so we'll put H2O with a gaseous phase. Another example would be ethanol, C2H5OH. So this is an example of a compound containing carbon, hydrogen, and oxygen. When ethanol reacts with oxygen gas, it too can create carbon dioxide and water, assuming there is sufficient oxygen gas to react with it in the first place. Otherwise, carbon monoxide could be created as well, which is not a good gas to deal with. But with sufficient oxygen gas, this reaction will go to completion and you'll get carbon dioxide and water. So those are examples of combustion reactions. Combustion reactions are very exothermic, which means they release a lot of thermal energy. When you react gasoline with oxygen, let's say in a combustion engine, it will generate a lot of energy, a lot of heat energy. And some of that energy is used to power the car to make it move forward. And so combustion reactions are very useful in terms of everyday applications. Now let's move on to the next type of reaction that we need to consider, and that is single replacement reactions. In a single replacement reaction, you have the general formula A plus BC turns into AC plus B. So what happens is, in this example, A displaces B out of the compound. And so B leaves, it's now by itself. So let me give you an example. In this case, for this type of chemical reaction, you're going to have a metal displacing another metal out of a compound. So zinc metal reacts with copper chloride, that is aqueous copper chloride, which means it's dissolved in water, to produce aqueous zinc chloride plus copper metal. So notice that zinc displaced copper out of the solution. So now zinc is in the solution, copper is now a metal, a solid metal that is not dissolved in the solution anymore. And so that is a single replacement reaction. Zinc replaced copper out of the solution, or kicked it out of the solution if you want to say that. Now, there's another type of single replacement reaction. In this example, we considered a metal replacing another metal. You can also have the situation where a nonmetal replaces another nonmetal. The general reaction for this type of situation is going to be A plus BC, and that's going to turn into BA plus C. So in this example, A, let me use a different color, A is going to displace C out of the solution. So here's an example. Let's say we have liquid bromine in its elemental form, and we're going to react that with a solution of sodium iodide. In this reaction, notice that bromine and iodine, or in this case, it's in the form of known as iodide. Both of these are nonmetals. Bromine and iodine they're not metallic. So bromine is not going to displace sodium because sodium is a metal. Bromine is going to displace another nonmetal like itself, in this case, iodine. So what we're going to get is sodium bromide, which is in an aqueous form, plus elemental iodine, which is a solid. So in this case, we have a nonmetal displacing another nonmetal out of the solution. That's the second type of situation that you'll see when dealing with a single replacement reaction. Now, the next type of reaction we need to consider is a double replacement reaction. In this reaction, we have AB reacting with CD. Now, what are the products that you think we're going to get? Now, notice the keyword double replacement. The two middle ones will come together, that's B and C, but it's going to be written as CB, not BC. And the two parts that are on the outside, they're going to pair up together, and it's going to produce AD. So those are the products of a double replacement reaction. Let me give you an example. Aqueous calcium chloride reacts with aqueous sodium nitrate to produce aqueous calcium nitrate plus aqueous sodium chloride. So this is an example of a double replacement reaction. We can see that calcium paired up with nitrate. In this case, this would be AD. I have them switched around for some reason. And sodium paired up with chlorine, as we can see NaCl. So notice that Na is written first. This is actually Cb. Cl is written later. If you break this up into ions, you'll have calcium 2 plus, you'll have the chloride ion, Na plus, and the nitrate ion. Notice that the positive ions are written first. So that's why sodium is written before chloride, because it has the positive charge. Calcium doesn't want to pair up with sodium because like charges repel. That's why calcium pairs up with nitrate, because they're opposite charges. Calcium has a 2 plus charge, Nitrate has a -1 charge. Ions with opposite charges will attract each other. And that's why sodium is attracted to chloride, because they have opposite charges. So you shouldn't see calcium paired up with sodium. They have the same charge. That's not going to happen. And you shouldn't see chloride paired up with nitrate. That's not going to be correct. Now, there are some other types of displacement reactions, or rather double replacement reactions, that you need to be familiar. And some of these have special names. Consider this one. Let's say if we react calcium nitrate with sodium phosphate. Both of these compounds are in the aqueous phase, which means they dissolve in water. They're water soluble. Now this is going to produce sodium nitrate, which also dissolves in water, plus calcium phosphate. Now calcium phosphate is not water soluble. It is insoluble in water, which means it doesn't dissolve in water. Now this reaction will be visible. The other reaction is not visible because everything was in the aqueous phase. But for this one, notice that we get a solid product. Whenever you mix two aqueous solutions, and if it produces a solid product, then the double replacement reaction has another name. And that name is a precipitation reaction. Calcium phosphate precipitated out of the solution. So this is an example of a precipitation reaction. You may learn this later if you haven't learned it already, but at least now you know what it is. Here's another one. If we take sodium sulfide in its aqueous phase and react it with hydrochloric acid, this is going to create sodium chloride, which will also be in the aqueous phase, but we'll also get something something else, H2S, hydrosulfuric acid. And this is a gas. So notice that not everything is in the aqueous phase. We're mixing two aqueous solutions, and we're getting not a solid product, but a gaseous product. So this type of reaction, even though it is a double replacement reaction, sodium paired up with chlorine, hydrogen paired up with sulfur, even though it's a double replacement reaction, it also has another name. And that name is known as a gas evolution reaction, because a gas evolved out of the solution. So that is a gas evolution reaction, another type of double replacement reaction. And for those of you who are curious, there is another type of double replacement reaction. And here it is. Let's say we react hydrochloric acid with sodium hydroxide. In this example, sodium will pair up with chlorine, forming table salt, sodium chloride. And then hydrogen is going to pair up with hydroxide, forming water. Now, water is not a solid, it's not a gas, but it's a liquid. So what do you call this? This is still a double replacement reaction, but it also has another name. And the name for this reaction is an acid-base neutralization reaction. Why is it called that? Well, HCl is an acid, hydrochloric acid. Sodium hydroxide is a very strong base. Whenever you mix an acid and a base, specifically a strong acid and a strong base, they will neutralize each other creating salt and water. And that's all, folks. That is the end of this lesson. So for those of you who found it to be helpful and very informative, make sure to hit that subscribe button, double tap it if you have to, and click on that notification bell. So thanks again. In this video, we are going to talk about how to calculate the theoretical and percent yield of a compound. So the first thing we need to do is write a balanced chemical equation. So we have C3H8, which stands for propane, and it's burning air, so it's going to react with oxygen gas, and it's going to produce carbon dioxide, and the other product is water. The reason being, it's a combustion reaction. You always get CO2 and water as products. So now we got to balance it. Whenever you want to balance a combustion reaction, you want to balance the number of carbon atoms first. We have 3 carbons on the left, so we're going to put in 3 in front of CO2. Next, we're going to balance the hydrogen atoms. So we have 8 on the left, 2 on the right. We know 4 times 2 is 8. And then finally, we need to balance the oxygen atoms. We have 6 oxygen atoms in the 3 CO2 molecules, 4 on the right from H2O, that's 10. 10 divided by 2 is 5, so we need to put a 5 in front of O2. So now the reaction is balanced. Okay, let's make a list of what we know. We have 30 grams of propane. Now, it's burned in air, so we can assume that we have an excess amount of oxygen. Whenever you have 2 reactants, you need to identify what's the limiting reactant and what's the excess reactant. You always want to use the limiting reactant to calculate your theoretical and percent yield, never the excess reactant. Now, the equation for percent yield, it is the actual yield divided by the theoretical yield times 100%. So you need to know the difference between the actual and the theoretical yield. The theoretical yield is what you calculate. It's the maximum amount of product that you can get. So if your reaction is 100% efficient, the amount that you get is the theoretical yield. In actuality, you know, you never get 100% yield. It could be 80%, 70%, it's never perfect. The actual amount that you get in a reaction, that's your actual yield. So the actual yield is usually given to you in a problem unless they want you to solve for it. And the actual yield usually is the grams of product. You see how we want to find the percent yield of CO2? That means that we need to use the actual yield of CO2 and the theoretical yield. They gave us the actual yield of CO2. They said, 70 grams of carbon dioxide was produced. That's how much we actually got in the experiment. So we know the actual yield. What we don't know is the theoretical yield, the most that we can get from the experiment. So let's calculate the theoretical yield, the maximum amount of CO2 that is possible to get. So we're going to start with the 30 grams of propane. We're going to see how many grams of CO2 can be produced at most from 30 grams of C3H8. So let's start with 30 grams of C3H8. The first step is to convert to moles using molar ratio. So the molar mass of C3H8, which we get from the periodic table, it's about 44 grams per 1 mole. Carbon has an atomic weight of 12, so 12 times 3 is 36. Hydrogen is about 1, and there's 8 of them, so 8 plus 36, you get 44. Now you want to do this in such a way that the grams of C3H8, they cancel. The next thing you want to do is you want to change the substance. You want to convert from moles of C3H8 to moles of CO2. Whenever you want to change from one substance to another substance, you need to use the molar ratio. And the molar ratio, it's a 1 to 3. For every 1 mole of C3H8 that burns in a reaction, 3 moles of CO2 are produced. And since we have moles of C3H8 on the top left, we need to put that on the bottom right so that they cancel. And therefore, the moles of CO2 will go on top. And then we simply add the numbers. There's a 1 in front of the C3H8, so we're going to put that here. And there's a 3 in front of the CO2, so we'll put that there as well. So moles of C3H8, they cancel now. The last step is to convert from moles back to grams. Whenever you convert from grams to moles or moles to grams, you need to use the molar mass in the periodic table, which is the same as the atomic mass. Carbon has an atomic mass of 12, oxygen is 16, and there's 2 of them, so that's 32 plus 12, that's 44. Now, because we have moles of CO2 on the top left, we need to put moles of CO2 on the bottom right. We want those units to cancel. So therefore, grams of CO2 has to go on top. And we said the molar mass of CO2 is 44. So that means that there's 44 grams of CO2 per 1 mole. So now we can do the calculation. So the numbers on top you multiply and you divide by the numbers on the bottom. So 30 divided by 44 times 3 times 44. So this gives us a theoretical yield of 90 grams. So what this means is that if all of the 30 grams of C3H8, if all of that reacts, the most that we can get, the maximum amount of CO2 that can be produced in this reaction is 90 grams of CO2. So that's what the theoretical yield means, the maximum amount that you can get. Well, in this reaction, we only got 70. So now that we have the theoretical yield, we can find the percent yield. So the percent yield is going to be 70 divided by 90 is always the smaller number divided by the large number times 100%. And that is going to equal 77.7% or 77.8%. So that's the percent yield of this reaction. That's how you find it. So that's it. That's all I got for you today. In this video, we're going to talk about equilibrium, but within the context of chemistry. So what is equilibrium? Well, let's say we have a reversible reaction where A can convert to B and B can convert to A. Equilibrium occurs when the rate of the forward reaction, that is A going into B, is equal to the rate of the reverse reaction. When these two rates are equal, the concentration of A and B will be constant. There's not going to be any net change. And so that's when we have a case of equilibrium, where the concentration of A and B are not changing because the rate of the forward reaction is equal to the rate of the reverse reaction. Chemical equilibrium is a form of dynamic equilibrium. It's not static because things are happening. Even though a system may be at equilibrium, the reaction is still occurring. A is converting into B, B is converted back into A. So we still have a reaction, but the concentrations of A and B are no longer changing at equilibrium. So we have a case of dynamic equilibrium. Now to illustrate this concept, let's say we have two cities. On the left, we'll call this city A. On the right, city B. Now let's say that city A has 1,000 cars. And we're going to say that city B has 2,000 cars. And let's say connecting these two cities is a highway. And on average, each hour, 10 cars travel from city A to city B. And each hour, let's say that 10 cars travel from B to A. So we could say that the rate of the forward reaction is 10 cars per hour. and the rate of the reverse reaction is also 10 cars per hour. So if each hour 10 cars is going from A to B and 10 cars is going from B to A, will the number of cars in city A and B change? The answer is no, because if A loses 10 cars each hour, but also gains 10 cars each hour, the total number of cars in A is going to remain constant. The same is true for B. These two don't have to be equal, but at equilibrium, the concentration of A and B are no longer changing. It's constant. And so that's what happens when a reaction is at equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction. And at that point, the concentrations of A and B are no longer changing. Another way in which we could visually show this concept is by the use of a concentration profile. So this is going to be a graph with the concentration of the reactants on the y-axis and time on the x-axis. So we're going to put A in red. Let's say initially we put 1 mole of A inside a container of a fixed volume, and there's no quantities of B in this container. So initially, if we only have A and no B, the reaction has to go to the right. It can't go to the left because there's no B to convert into A. So that's what's happening initially. If we put 1 mole of A, let's say in a 1-liter container. As the reaction goes to the right, the concentration of A is going to decrease over time. The concentration of B is going to increase. So A is going to decrease. It's not going to go to 0, but eventually it will become constant. B starts from 0 and then it increases. B becomes constant when A becomes constant. When A stops decreasing, B will stop increasing. Now the point where the concentration no longer changes, that's where we have a case of dynamic equilibrium. So whenever the concentration of A and B, when it becomes horizontal in this graph, that means it's not changing anymore. At that point, the rate of the forward reaction equals the rate of the reverse reaction. And so they're equal at that point. So now let's plot a graph that shows the rate of the forward reaction and the rate of the reverse reaction. So we're going to put the reaction rate on the y-axis, time on the x-axis. So the rate of the forward reaction is equal to K1 times the concentration of A. As the reaction goes to the right, A is going to decrease. And as A decreases, the rate of the forward reaction is going to decrease. So initially, the rate of the forward reaction is going to start at a high, and then it's going to decrease over time. Let me draw that better. And eventually it's going to be constant. Now, as A decreases, we know B is going to increase. And the rate of the reverse reaction is dependent on the concentration of B. It's K negative 1, that's the reverse rate constant, or the rate constant for the reverse reaction, times B. So as B goes up, the rate of the reverse reaction is also going to go up. So I'm going to put that in blue. Now, eventually, the rate of the forward reaction is going to equal the rate of the reverse reaction, which it does here. So at that point, we've reached a state of equilibrium. Once the rate of the forward reaction equals the rate of the reverse reaction, A is no longer decreasing, B is no longer increasing. The concentration of A and B will be constant at that point. So if we set the rate of the forward reaction equal to the rate of the reverse reaction, which occurs at equilibrium, we can say that K1 times A is equal to K negative 1 times B. I'm going to divide both sides by A and K negative 1. So these will cancel and those will cancel. And so K1 over K negative 1 is going to be B over A. The equilibrium constant K is equal to the concentration of the products divided by the reactants. So therefore, the equilibrium constant K is also equal to the ratio of the forward rate constant divided by the reverse rate constant. The equilibrium constant K is represented by capital K. The rate constant is indicated by lowercase k. So make sure you remember this. The equilibrium constant K is equal to the forward rate constant divided by the reverse rate constant. And it's also equal to the ratio of the products divided by the ratio of the reactants. The coefficients in this case is 1. The coefficients become exponents in the equilibrium expression. Now let's work on some practice problems. Number 1, write the equilibrium expression Kc and Kp for the following reaction. Now there's two types of equilibrium constants you need to be familiar with, Kc and Kp. Kc is for concentration, Kp is associated with partial pressure. So this is the equilibrium concentration constant, that's the equilibrium partial pressure constant. Now to do this, you need to be familiar with the law of mass action. So let's say we have A plus B reacting to produce C and D. And let's say the coefficients are J, K, L, M. To write the equilibrium expression, when you see K or KEQ, it's typically associated with KC. So KEQ is going to be the concentration of C times the concentration of D divided by the concentration of A times the concentration of B. It's basically the concentration of the products divided by the concentration of the reactants. Now the coefficients become exponents in the equilibrium expression. So that's the equilibrium expression for this reaction using the law of mass action. Now let's do the same thing for Kc and Kp. So Kc is going to be equal to the concentration of the products divided by the concentration of the reactants. And then the coefficients will become exponents. So there's a 2 in front of NH3, so we're going to put that on the exponent of NH3. And this is going to be to the first power. And for H2, we have a 3. So that's how we can write the equilibrium expression for Kc. The square brackets indicates concentration. Now, to write the equilibrium partial pressure constant, Kp, it's going to be the partial pressure of the products, in this case NH3, and that's going to be raised to the second power due to that coefficient, divided by the partial pressure of N2, that's going to be raised to the first power, and then times the partial pressure of H2, which will be raised to the third power. So that's how we can write the equilibrium expression for Kp based on this reaction. Number 2, nitrogen reacts with chlorine to produce nitrogen trichloride. At equilibrium, the concentrations of each gas were found to be 0.15, 0.25, and 0.50 molar. Calculate the value of the equilibrium constant Kc. By the way, if you see problems that ask you to calculate K or KEQ, this typically refers to Kc. Unless specified otherwise, always go for Kc. If it specifically asks for Kp or the equilibrium partial pressure constant, then you use Kp. If you see K or KEQ, it typically corresponds to Kc. So just keep that in mind. So before we can calculate Kc, we need to write a balanced reaction. Nitrogen is a diatomic gas. Chlorine is also a diatomic gas. And this is going to become nitrogen trichloride, so NCl3. Now we need to balance the chemical equation. We have 2 nitrogen atoms on the left. We need to put a 2 in front of NCl3, so we have 2 nitrogen atoms on both sides. Now we have a total of 6 chlorine atoms on the right side. If we divide that by 2, that tells us that we need to put a 3 in front of Cl2. So now we have a balanced chemical equation. So let's write the expression for Kc. It's going to be the concentration of the products divided by the concentration of the reactants. And the coefficients will become exponents. Now remember, at equilibrium, the concentrations of the reactants and the products are no longer changing. And since we have the concentrations at equilibrium, we can just go ahead and plug it in to get the value for Kc. So the concentration of NCl3, that's 0.5. The concentration of N2 is 0.15. And the concentration of Cl2 is 0.25 moles per liter. And that needs to be cubed. So when you're plugging this in, you may want to put an extra set of parentheses in the denominator. Otherwise, your calculator may divide by this number, but may multiply by 0.25 to the third power. So I recommend enclosing that entire thing in parentheses. So let's go ahead and get the answer. So Kc is going to be 106.6 repeated. So that's the value of the equilibrium constant, Kc, in this example problem. Number 3, Sulfur dioxide reacts with oxygen gas to produce sulfur trioxide. At equilibrium, the partial pressures of each gas were found to be 0.10 atm, 0.30, and 0.45 for SO2, O2, and SO3 respectively. Calculate the equilibrium constant Kp. Well, let's begin by writing a balanced chemical equation. So we have sulfur dioxide, SO2. It's going to react with oxygen gas, O2, and it's going to produce sulfur trioxide, SO3. So all of these are in the gas phase. So to balance it, right now we have equal number of sulfur atoms, but we're going to have to multiply it by 2. Here we have 4 oxygen atoms, plus 2, that's 6, and 2 times 3 is 6. So we have 6 oxygen atoms on both sides. Let's put a 1 in front of O2. So now the chemical equation is balanced. Now, let's write an expression for Kp. So Kp is going to be the partial pressures of the products over the reactants. So we're going to have the partial pressure of SO3, and this is going to be raised to the second power, divided by partial pressure of SO2 raised to the second power, times the partial pressure of O2 raised to the first power. So the partial pressure for SO3, that's going to be 0.45 atm. Now the partial pressure for SO2, that's 0.10 atm. And for O3, it's 0.30. So let's go ahead and plug this in. And let's put this in one set of brackets or parentheses. So it's 0.45 squared divided by 0.10 squared. And then you could take that result divided by 0.30. So you should get 67.5. So that's the value of Kp in this example problem. Number 4, if Kc for the reaction shown below is 9.6 at 300 Celsius, what is the value of Kp at this temperature? Now this is a formula that we could use to go from Kp to Kc or vice versa. But let's talk about how to get that formula. So let's say we have a generic reaction, A plus B turns into C plus D. And we're going to have our generic coefficients, J, K, L, and M. Let's write the equilibrium partial pressure expression for this reaction. So Kp is going to be the partial pressure of the products, so the partial pressure of C, and that's going to be raised to the L power, times the partial pressure of D raised to the M power, and that's going to be divided by the partial pressure of A raised to the J power, and then times the partial pressure of B raised to the K power. Now, based on the ideal gas law equation, we know that PV is equal to nRT. So if we divide both sides by the volume V, we get P is equal to nRT over V. But instead of writing it that way, we can write it like this, N over V. Because concentration is moles divided by volume. So we can replace N over V with C. So we get the pressure is equal to the concentration times RT. So I'm just going to rewrite that here. So now what we're going to do is we're going to replace P with CRT in this expression. So the partial pressure of C, we can replace that with the concentration of C times RT, and it's going to be raised to the same exponent, L. So let's do the same for the rest. So the partial pressure of D is going to be the concentration of D times RT. The partial pressure of A is going to be the concentration of A times RT. And the same is true for the partial pressure of B. That's going to be the concentration of B times RT. And let's put the exponents, M, J, and K. So now what we're going to do at this point is we're going to separate the concentration from RT. The concentration of C, we can simply put it in brackets. It will be just C. But let me rewrite this over here. So keep in mind, this whole thing is still equal to Kp. We can delete this as well. Actually, let's keep that for now. So this is going to be the concentration of C, and then times RT. This is going to be the concentration of D times RT. Now keep in mind, this is raised to the L. So this is the concentration of C raised to the L, and the concentration of RT raised to the L. And then this is the concentration of D raised to the M times the concentration of RT raised to the M. You have to distribute the M to both D and RT. Now the concentration of A, we can simply just put that in brackets as well, and then times RT, and those two will be raised to the J power. And then we have the concentration of B, which is raised to the K power, times RT, which is also raised to the K power. And this is still equal to Kp. Now what I'm going to do is I'm going to break this fraction into two smaller fractions. In one fraction, I'm going to collect all of the concentration terms, and then in the other fraction, all of the RT terms.
Okay. Iwasan lang ni ugma guys kay taas pag yung kayo siya no. Doon na patay usa ka lecture ni ang katong ato ang ano the number of moles that will be reacting no forming into product no. Importante ito nato siya nga mapi sa atong review. So di na to mahuman. We'll finish this tomorrow siguradong mahuman nga to ni. Okay, so we'll just cut this at this time. We'll be having our second attendant. Please open your microphone. Abarkis,
Present, sir.
Abrasaldo,
Present, sir.
Chita,
Present, sir.
Arong,
Present, sir.
Darius,
Present, sir.
Silvestre,
Present, sir.
Cañete,
Present, sir.
Caballero,
Present, sir.
Castañares,
Present, si Castañares, sir. Nag-ulan daw sila, sir. Present, sir.
naon sa sila? Hello?
Present, sir.
Castañares. Coyos, I mean Clemente.
Present, sir.
Coyos,
Present, sir.
Lakay,
Present, sir.
Inglasa,
Present, sir.
Dinopol, Dinopol Jade,
Present, sir.
Durham,
Present, sir.
Cario, Cario Jan,
Present, sir.
Obreke,
Present, sir.
Figueroa,
Present, sir.
Juliana,
Present, sir.
Darina,
Present, sir.
Uma, Lagruma,
Sir. Present, sir.
Leopando,
Present.
Luab, Luab, huwag tang
Sir,
salut.
nawala ko ng connection ni Luap. Bago lang, sir. Bago lang nawa yung internet.
Naguwan dia sa inyo ha? Kay pirtang kusog ang uwan dire.
Yes,
Yes,
sir.
sir.
Gauwan
One,
sa
sir.
Mindanao.
Pasas Mindanao naguwan pod.
Yes, sir.
Lumibaw. Lumibaw. Unsa may status ni Lumibaw? Ha?
Connecting sa Goro to siya, sir.
Nara si Luibaw, sir.
Okay.
Sir.
Miole.
Present,
Miole
sir.
Samantha. Morok.
Present, sir.
Okay.
Present,
Morok.
sir.
Nervida.
Present, sir. Navida.
Palis.
Present, sir.
Pipito.
Present, sir.
Perez.
Present, sir. Perez.
Randas. Randas.
Present, sir.
Reponte.
Present, sir.
Ruben. Ruben.
Naa si Ruben, sir. Hinay ang net.
Sanoy.
Present, sir.
Sinilio. Sinilio
Present,
Kenneth.
sir. Sinilio.
Suson.
Present, sir.
Okay.
Present, sir, Susan.
Toledo.
Present, sir.
Vergara.
Present, sir.
Yaon. Franklin.
Present, sir.
Okay, so that's it guys. By the way, si kisa to si Jade, no? Jade Dinopol. Okay. Doon na tayo kuan sa na Jade mag-chat na ako nimo ha. Kay doon na ipa buhat si Ma'am Amis. Okay. Okay, so I hope nga na-recall na ninyo ato ang kuano chemical reaction kinetics. So by do napatay kuwang nato no aron gyud insakto nga ato ang kuan, sakto atong bala or ato ang preparation para sa designing sa ato ang kuan no, mga reactor no. So that's it guys. If you have no more questions, you can log out now. God bless.
Thank you,
Thank you,
sir.
sir.
Thank you, sir. Thank you, sir.
Okay.